Okay, so today we're going to be starting a new section on errors. So last time we looked at errors in terms of linear and quadratic approximations and the errors involved in using those approximations. This one's a little bit different. So we're going to be estimating errors involved in measurement. So when you do your physics pracs, you measure some things, there's some error involved. We're going to use this technique here to estimate the error involved in the final outcome. For example, say you're measuring the voltage, you measure the resistance, it's not accurate, right? There's some error. You measure the current, again, not accurate, there's some error. How does the error in the resistance and the current end up being an error in the voltage? So there's some input error, there's going to be some output error. How do we relate the two? So when you do your physics pracs, you can use this. So when the pre-prac says, what's the expected error in this thing, you can go ahead and use this for those. Okay, so we're going to start with a very, very simple problem, just to get the idea of where this comes from. Then we'll look at some more difficult problems. Okay, so none of the problems are difficult, it's just a little bit more difficult. Now, just a little word of warning on differentials. If you're going to go home and Google this or ask ChatGPT or Gemini or whatever about differentials, please make sure you look at the right thing. So when you're Googling math differentials or something like that, there's going to be the stuff that we're covering, okay, Calc 1 differentials, if you want to write that down. There's another thing called differentials in math, differential forms. Okay, same name, they're both called differentials. One is very simple, the other is very, very scary. Please do not look at that. Okay, so if you're Googling this and you see differential forms, ignore that. Okay, very, very scary stuff. You don't want to be looking at that now. Okay, so just be careful when you're looking at these differential problems online. Okay, so the first example is going to be very easy. We're going to be measuring the area of a square. And our ruler is not so good, there's going to be some error involved. Okay, so we've got ourselves a square. Okay, so we know it's a square. It has some expected side length. Let's call it S. So S and S. So if our ruler was perfect, we would measure the area S squared. Yeah, so straightforward. Now, like I said, our ruler is not so good, there's some error involved. So maybe this side, maybe it's a little bit more than it should be. On the other side, maybe it's a little bit more than it should be. Okay, so there's a little bit extra added on because our ruler is not so good. Okay, so we have something like that. We have the exact result. We know it should be this white area, but because our ruler is not so good, we have this additional pink area that we measure. So this white part, this is what it should be, S squared, but there's a little bit extra there. Now the whole idea is, what is that pink area? What is the error involved in the measurements? So we're going to treat this, like I said before, we have some input. That's going to be S. This is what we're measuring. So the input has some error, delta S. That's the error we put in. The output error, that will be delta A. That's the error involved in the area. So what is delta A? So this is the output error for the input error delta S. Okay. This delta A, we want to work that out. We're going to do it two different ways. The first way is the exact error. So remember yesterday I told you exact error, relative error, percentage error, all of that. I hope you looked through that. So we're going to find the exact error. In other words, the exact area in pink. What is that exactly? Now we're going to see that involves quite a bit of work. We don't want to do the work. So instead, we're going to estimate it. And we'll see the estimate is actually pretty good in most situations. Okay, so what will it be exactly? The exact error will be this larger area where we use S plus delta S, the bigger square, minus the smaller square. Right? That will give us this pink region. So the exact error delta A will be the area where we include the error minus the area where we don't include the error. Okay, that will be the pink region that we're interested in. Okay, so let's work it out. We'll see it's a little bit of work. And then after this, we'll see how we can skip all of this steps here. Okay, so the full one, it's an area of a square. We know how that works. It's just the side squared. And then the area of just the square with side length S is just S squared. Okay, so this is equal to, we can expand this out. So we have S squared plus 2S delta S plus delta S squared. Okay, so that's just expanding that out there. And then minus S squared. So S squared minus S squared, that cancels. We're left with 2S delta S plus delta S squared. So given the true shape, whatever it is, so we know what it should be. We know the error, right? We know the ruler is off by so much. We can input what we expect. We can input the error, and that will give us the exact error in measuring the area. And this is exact. No approximations, nothing like that. This is exactly what we get. Okay, so this is delta A. Okay, now we're going to do some estimating. So instead of doing all this work, expanding the squares, we don't want to do that. We're going to instead estimate this. Okay, yeah. Yeah? Why did we square it? How do you find the area of a square? Side times side. Okay. Okay. Now we're going to find an estimate for the error. Okay, so again, this is the exact error. Now we're going to find an estimate for the error, and we'll see it's pretty close, right? It can't be exact because it's an estimate, but it's good enough. So we're going to start by looking at the definition for the derivative. Seems a bit strange, but we'll see how that works. So we've got our function a of s is equal to s squared, right? If you've got a square, you know the side length, you know the area. So we've got that. Now, what is the definition for the derivative of a? A prime will be the limit. I'm going to write it a little bit different. Instead of writing, f of x plus h over h, instead of h, I'm going to use delta s. So it's exactly the same idea as the derivative we did all those weeks ago. So let's say we've got our function a of s. Okay, we're interested in some points over here. So instead of moving h over, I'm moving delta s over. It's the same idea. same idea. So instead of using h, I'm just going to call it delta s. Why? Well, I called this delta s over here. Okay, it's going to end up being the same delta s we used above. Okay, now in the limit, these sides are exactly the same. Okay, so if we take the limit delta s goes to 0, this side is just the definition for that left-hand side. If we don't take the limit, it's not going to be the tangent line over here. It will be that secant line. It's an approximation to the tangent line. So this secant line through the 2 points, that will be an approximation to the tangent line. So here we have A prime is approximately, it's not exactly, it's approximately A of S plus delta S minus A of S over delta S. So again, the first line, that was for the tangent line. That's exactly at a point. The second one, because we're not taking the limit, this is the secant line. It's an approximation to it. Okay. Next, I'm going to take this delta S over to the other side. I'm going to stop writing the squiggle, but it's, again, still an approximation. So I'm going to take this over. I'm going to keep this on one side. Yeah. But what is this on this left-hand side? From the previous working, this is the exact error, right? The area with the error minus this, that's the exact error. Okay, okay, I'll put the approximation one more time, but then we'll stop doing that. Okay, so this over here is definitely equals. This is definitely the exact error. And over here, it is approximately equal to this over here. Okay, so we're going to use this formula to work out an estimate for delta A. Again, squiggly equals, it's an estimate. And we're going to compare it to what we had originally. Okay, now I'm going to drop the squiggles. Okay, we'll keep it as an equals there. Is equal to A prime of S delta S. So remember, A of S was S squared. So what's A prime? 2S. Okay. And we end up with this. Now notice the difference between this and what we had earlier. This is the exact error. It was 2S delta S plus delta S squared. This was our estimate using the derivative. So we approximate the function using the tangent line. It's a linear approximation from what we did yesterday. So using this linear approximation, we get this error, but it's missing a delta S squared. Okay. So this is the estimate. So the difference between the estimate and the exact is this delta S squared over here. But it's not so bad, because what did we assume in our estimating over here? We assumed limit of delta S going to 0. We assumed delta S is very small. So if we look at our answer here, and we assume delta S is very small, delta S squared will be even smaller. Think about 0.1. If the error is 0.1, 0.1 squared is 0.01. It's even smaller. So this over here, in the limit delta S goes to 0, this kind of just goes away. Okay, so this is small. This is small. This is even smaller, so we kind of just throw it away. Okay, that's the idea. So in the exact error, we include this. In the estimating error, this is very small, we throw it away. We only keep the delta S terms over here. Is everyone clear on that? Okay. And by only including the delta S terms, it's just the linear approximation from what we had. This would then be quadratic. and so on. Okay, so given a function f of x, where we are measuring x with some error, let's call it delta x. Okay, so we're given some function we're measuring. Could be the area, could be a voltage for a circuit, chemistry, right? There's something that you're measuring, there's some error involved. Okay, so we're measuring f of x with some error delta x. The estimated error right? This is not exact, right? The first one was exact. This is always an estimate. So the estimated error for f of x is given by delta f. So whenever we have a delta, that means some error. So delta f is equal to f prime of x delta x. Okay, so from now on, we're going to drop the squiggly equals. So whenever you have a delta f, this is going to be the estimated error. Okay, so before we used the squiggle because this was the exact error. From now on, we always know that this is the estimated error, so it is an equals. So this delta f will always be the estimated error. Yeah, please put a box around that. We're going to be using this multiple times. Okay. Any questions for this? All clear. Okay. Let's have a look at some examples. Okay. The volume of a square-based prism, or square-sided prism. Okay, so you know what your prisms and cones and that. So a square-sided prism is just a square box. Has a side length of 20 centimeters. But there is an error in measurement of 0.1 centimeters. Yeah. So we're measuring this box here. Has a side length 20. Our rule is not so good. We've got an error of 0.1. What is the error in our measurements of the volume? So we're going to do this two ways. So in class, we're going to do the estimating method to get some answer. For homework, you're going to find the exact error and you're going to compare the two, see how close we are. Okay, so number one, the estimates of the error. So estimating the error using differentials. Okay. So let's see what that's going to be. So the volume, let's call that V. So we're going to have delta V. Will be V prime of X delta X. Okay. Same as we had before with the F prime. So we measure X. We've got some error in X. What's the error in the volume? Okay, so just a note, none of these functions will be given. So you're going to be given some word problem. You need to figure this out, what this is going to be. Okay. So it could be a very simple shape like this. Could be some complicated thing. You need to work it out. Okay, that's going to be part of the problem. In this case, it's very easy. It's the volume of a square cube. So the volume is just x cubed. Yeah. Again, very simple. Can be a bit more difficult than that. So v prime, what's that going to be? 3x squared. Yeah, very simple. Now we just substitute what we have there. So here we know that the side length should be 20. Error in measurement 0.1. That's going to be our delta x. That's going to be our x. So let's substitute, see what we get. Okay, a little calculator work. What do we get? $120, thank you. And the units? Right, there's units all over the place here, centimeters cubed. Right, because x is centimeters, so this will be centimeters squared. That will be another centimeters cubed. Okay, please remember your units for these problems. All right. Any questions for this one? All good. Okay, so the second part, the actual error, you're going to do that for homework. You're going to compare it to this. Okay, so the actual error, that will be, since there's this error of 0.1, it will be the larger volume minus the smaller volume. So it will be V x plus delta x minus V at x. So larger volume minus smaller volume. You can work that out, see what you get. Okay. Okay. And then just a side note on the relative error and percentage error. Did you all go through that from yesterday? Yes. Okay, good. So yeah, we got the error. Some follow-up questions could be, so this is the error. What's the relative error? Well, the follow-up question could be, what is the percentage error? Okay. So we won't do that here, but that could be some follow-up questions. Yeah. Number 2. The volume of a sphere is measured with some error. Okay. So again, we've got some shape here, a sphere. You need to know volume, surface area, all of those things. The diameter is measured to be 2 meters with an error of 0.5 centimeters. What is the error in measuring the volume? Yeah, so we've got our setup, we've got a sphere, we're measuring the diameter, there's some error in measuring the diameter. What is the error in measuring the volume? Okay, so we're going to set this up. We need an equation, so the volume. Now, it's not the 4/3 pi r cubed. That's not going to help us because we have the diameter, not the radius. So we need to do a little bit of changing for that. So the volume 4 over 3 pi r cubed. All right, that's not going to help us. We've got the diameter, and we've got the error in the diameter, not the radius. Okay, so we need to change this a bit. How do we get from diameter to the radius? Times 2. Divide by 2. I heard someone say times 2. Okay, careful with that. So the radius will be the diameter over 2. So if we substitute that in, that gives us the formula we need. Okay, so the volume, that's 4 over 3 pi. So instead of the radius, we want the diameter. So that will be d over 2 q. Okay, so 2 cubed, that's 8. We have at the bottom there. Okay, so 4 over. Yep. So we get the 8 from there. So 4 over 8, that's a half. So we're left with the 6 at the bottom. Okay, so we've got the correct formula now for the volume in terms of the diameter. So we want to estimate the error in the volume. So that's going to be delta V. So that will be V prime of D, not R, because we've got a new formula there. Then delta D. Okay, so V prime, we need to take the derivative of that formula we came up with. So we take the 3 down. So what will that be? Pi over 2 D squared. And then delta D, what's that going to be? No, not 0.5. Look at our units. The diameter was measured in meters. The error is given in centimeters. You can't add meters and centimeters together. Right? That doesn't work. So we need to do some conversion. So please make sure that your units match when you're substituting. Okay, so if you're going to work in meters for the measurement, your error should be the same. So 0.5 centimeters converted to meters. Hopefully everyone knows that. What do we do? Okay, thank goodness. Yeah, so we divide by 100. Okay, quick calculator work. What do we get for that? Oh, someone was very quick. What is it? 0 point? 0? 0.005. Okay, that's good enough. 3 decimal places. That's fine. The units? Meters, yeah. Because we did the conversion, so everything is in meters. Okay, good. Any questions for this one? Okay. So again, please be careful with that bit there. Any questions before we move on? Yeah? 0.03. Sorry, I can't hear you. What?
0.005 is the conversion.
Oh, why are you telling me it's the final answer? Okay, someone please tell me the right answer. 0 points? 0.031. Okay. I think someone's sabotaging the class. They won top place. They're making you all write the wrong thing. Okay, everyone okay with this one? This fine. Okay. Any questions before we move on? Yes.
We know they must need this.
3 is fine. Yeah. Yeah. So 2 decimal place. If it was 0.001, probably write it as 3. Otherwise, you're just writing 0. Yeah. So just see how many zeros you've got. So if it's 0.0 something, 2 decimal places is fine. If you want to do 3, that's fine. Please do not write more than 3. Yeah, I'm not going to check your answers for that. Okay. So 2 decimal places, 3. I'm not going to check 4 decimal places. All right. Any other questions? All good. Okay. So that's number 2, number 3. Okay. A person wants to paint the surface of a sphere. With radius 10 centimeters, such that the thickness of the layer of paint is 1 millimeter. Okay, estimate the amount of paint needed. So we have this problem here. It's not phrased in terms of an error problem. It's phrased in terms of an estimating problem. Okay, well, it's the same idea. You want to estimate the error or you want to estimate something else, we're going to use the same technique. Okay, so we got ourselves a sphere of radius 10. So we can do a little sketch of this. So we got ourselves a nice sphere there. It's got some radius. Okay. This person wants to paint it to a layer of 1 millimeter. So you imagine the sphere with some paint around it. It's going to increase the radius a tiny little bit. So let's say they want to paint it pink. So there's a little bit extra here going all the way around. Yeah, so it's going to look something like that. Obviously exaggerated a lot more than what it is. So you've got your sphere on the inside and then some layer of paint on the outside. We want to estimate how much paint did we use to paint this thing. So we're going to phrase it in terms of what we had before, some radius, some difference to the radius, delta R. So this little extra bit, delta R, we're adding on to the radius. And we want to estimate that pink volume that's around the sphere. Now, we're not going to do this exactly. We're going to do an estimate like we had before. So we're trying to estimate volume. So we need the volume of the sphere. We had that before. Okay, so we know the volume. So the delta V, that's that extra volume that we've painted on. So that will be V prime of R. And then delta R, that's that extra bit that we added on to the radius. Okay, so V prime, we take the 3 down, so 4 pi R squared delta R. Okay, everyone okay with this bit? Okay. A little bit of sanity check. This 4 pi R squared. What is that? That's the surface area. What do we get if we take the surface area times a little height? So area times a little height to it. What is that? That's the volume. Yeah. Yeah, so it makes sense. You look confused. Okay. Now you must have confidence in this. Yeah, it's the surface area. So we take the surface area times it by a little thickness, well, that's the extra volume we've added on. Yeah, so it makes sense for the formula. Let's substitute. So delta V is 4 pi r. Let's see what that was. 10 centimeters. There's a lot of talking going on. Okay, please keep it down. Okay, and then delta R, we've got a little issue here. Okay, it's in millimeters, but we measured this in centimeters. We need to do a bit of conversion. Okay, so 1 millimeter is 0.1, right? Okay, so 0.1 centimeters. Okay, please check your units again. Okay, a little bit of calculator work. What do we get for that? What's that? 45. Pi. No, decimal. 125,6. 663. Let's leave it like that. Yeah, you can leave it like that. That's fine. The units? Centimeters cubed. Yeah, I don't really care much about if you can round your answers or not. If I can see you know what you're doing and you're substituting fine, I trust your answer there. Okay. So we have something like this. Okay, but again, if you want all the decimal places, please stop at 3. After 3, you're wasting your time. Right. Any questions for this one? Okay. Very easy stuff. Okay, so in the tutorial, there's quite a few more problems like this to go through. Please do those problems. Good practice for the test. Okay. And then just the last thing for today, just to go through the dates for the rest of the semester. Okay, just to give you some perspective on what's left. So we are over, where are we? Over here, approximations. Okay, so we've finished now with the approximations. Okay, next week, Tuesday, we've got the practice June test. It's less marks than the June test, but I'll still give you the full tutorial period time. Okay, so you got the full time to do that. That will be on the Tuesday. Wednesday and Thursday, we'll do curve sketching with polynomials. That curve sketching is not like high school. Okay, please do not think it's sketching, your simple cubics and your parabolas. This will be 4th order and 5th order polynomials. Okay. Yeah, please do not think it's like high school. You got your cubic like this. You draw your cubic, yay, 10 marks. No, we're going to be drawing things like this. Things like that. So we've got inflection points, we've got turning points, and so on. This will be the easier one that we're going to be looking at. Okay, so that will be for next week. And then the week after, we're going to be doing sketching of rational functions. They're going to look something like this. So you got some asymptotes going on, maybe another asymptote like that. It's going to look something like that. Okay, so your hyperbola you drew in your grade 12 final, little bit like this, you got your 10 marks, yay. No, we got all this other stuff going on. Okay. This will be for the June test, something like this. Okay. So for these ones, we need to look at x-intercepts, y-intercepts, turning points, vertical asymptotes. See, now we've got 2 of them. High school, you only had 1 of them. We've got 2 of those. Horizontal asymptotes, inflection points, all of that stuff. Okay. These will be 10 marks. Okay. For your June test, 10 marks. And for your final exam, 10 marks. Okay. Now, just to put that in perspective, your final exam is out of 100. This question is 10 marks. You can do the math on that. Okay. So that's what we're going to be doing for those 2 weeks. This week over here, depending on how the sketching goes, I'm hoping to do some revision. So the way that's going to work is I'm going to put up a Google form with everything we've done so far from day 1 up to the curve sketching. There will be little buttons you push on what you want covered. You can select everything, you can select nothing, you select whatever you want. Then I'll tally up the results and we go from top to bottom during those days. Okay, so if everyone votes on L'Hopital's rule, we do that first. If no one votes set theory, I'll throw that out. We don't do it. Yeah, so it's entirely up to you as a class to vote on what we do. So this Tuesday, this quiz will be based on whatever you vote. It will be a mix of things we've covered. And the Wednesday, again, we just go top to bottom with some problems. Thursday, again, whatever's left over. After that, you're on your own. Okay, so please make sure you vote for the things that you need most help with. If it's a little side question, don't vote on it. Come and see me. Okay, there's not much time. Because straight after that, we got class test 2. Okay. Then after that, lectures end for the exams. Okay. That's not for you. That's for the second years. So you'll carry on with the other modules. I will give you that time off. It's not the same for the other lecturers. They might continue. Okay. But after the class test 2, I've got nothing more to teach you guys. So you'll be off from me. Please go to your other lectures. So you got 2 weeks off from me and then the June test. Okay. So class test, 2 weeks off, June test. Okay. So a little bit of revision time between that. And then straight after the June test, don't come and see me. You're off. You're going to have a bunch of weeks off. Okay, that's off from me, right? This time here, between this June test and first semester ends, you might have your physics June test, or you might have engineering or something like that. Okay, but you don't have me. No lectures during that time. Okay, then you got your break. Then we come back. Second semester, we got optimization, antiderivatives, area problem. This bit over here, these few weeks, these 3 weeks over here. Definite integral properties, FTC1, FTC2. FTC stands for Fundamental Theorem of Calculus. It's a very big section, covers 3 weeks. There are a lot of proofs, at least 10. Okay, at least 10 proofs. You will need to know them for the final exam. So I'm warning you now so you can prepare yourselves for that. So FTC1, theorem and proof. FTC2, theorem and proof. Properties of definite integrals, there's about 10. Theorem and proof. A lot of proofs for that. Then we have revision, class test 3. Then we're done. A few more things, class test 4. Okay. End of October, we have our class test 4. And then you have your final exam somewhere here. I can't tell you the final exam date. That's done through the university. Okay, so you have to check the university website for that. So your final exam could be on the 2nd of November, or your final exam could be on the 1st of December. Somewhere between there, you have your final exam. I cannot move the exam. I cannot tell you when it is. It is up to the university. If they want to put your final exam over here after doing class test 4, tough luck, that's how it is. Okay. Over here, you will also have your final exam for physics, somewhere there in November, and for your other modules as well. Okay, engineering might have exams. You need to check for that. Okay, so that's the perspective for the remainder of the year. Any questions for that? So end of this semester, we'll finish up with the applications. Class test 2. Next semester, term 3 and 4, proofs. A lot of proofs, a lot of working. Please prepare for that. Okay, any questions? Oh, good. Okay, so we'll leave it at that